Hello. Today we are going to start the main chapter 1, and the first chapter is about probability. Let me start. Before we start, let me overview what we are going to do throughout the semester. So, as I said in the introductory videos, there are 12 chapters in this course, and I can divide the 12 chapters into 4 main parts. The first part is what we're going to do from now, and it covers from chapter 1 through 4, and this is about descriptive statistics. It literally means how to describe some random object, and simply speaking, it's about how we can understand probability, mean, variance, standard deviation, something like that. So it is literally about description of data. And the second part is about distribution models. Model is a simplification of phenomena using a few assumptions. So this is a typical way of science studies, like natural sciences. We observe something and we extract some key assumptions from the phenomena and observations, and based on those simplifications, we can understand the phenomena better, and we can predict what's going on like in the future, or study the properties of what we observe. And then the third part is from chapter 8 to 10. This is about inferential statistics. The first two parts are more theoretical, but chapter 8 to 10 is what we actually call statistics, like estimation, hypothesis testing. So maybe the statistics, like in your mind, is more like chapter 8 to 10. And the last two chapters are about linear regression model, which is the workhorse model in economics and maybe in any social science. So linear regression model accounts for, I believe, more than 90% of data work in economics. So so linear regression itself is a topic for another semester, whole semester. So I cannot cover all the linear regression model in here in this course, but I will briefly introduce what you are going to do in the next step if you take another related course in data analysis, quantitative methods, statistics, or econometrics. Then it must start from the linear regression model. So I will touch that topic briefly in the last part. Okay, so let's come back to part 1, descriptive statistics. As I said, we learn how to describe data and how to characterize random objects. And simply speaking, there are two major building blocks in any statistics. The first one is the probability, and the other is the average. Exactly, the probability and the average are what you know. The things that you know are the major building blocks. And roughly speaking, I can say any statistics is a kind of, any statistical method is a kind of variation of one of these two. Right? It can be, so any statistical method is based on some probability or some kind of average. So these two are two most important concepts in statistics. So we are going to make the fundamental concepts in these chapters. Okay. So by the way, this part, I think the first 4 chapters are the most important, practically and theoretically, but many textbooks have different organizations. Most textbooks are organized in a different way. So it's hard to find what I'm teaching from the textbook. So I don't like any textbook about in this chapter. So but by the way, but if you are interested in further reading, or if you want to compare with your textbook, you can refer to those chapters. By the way, like newest edition may change the chapter numbers, but I believe it shouldn't be a big difference. So here, this is what we are going to do in this chapter, in the first chapter. So let me start with how we can make a structure to define a probability. So we will make a framework to study probability. So let's start from the simplest possible probability. So probability is exactly what you have in mind. So let's think about this. The simplest example is the coin toss. When you toss a coin, the probability of a head is 50%. Right? So it's obviously, trivially correct sentence, or probability sentence. And then, now let's delve into what kind of structures are behind this sentence. In this sentence, three main essential components about probability are, first, 50%. So this is the probability, right? So probability is 50%, not a problem. Also, you defined an experiment. So when you talk about probability, you have to define or the underlying experiment, where the probability is coming from. If it was not a coin, or if it was like a different shaped, like dice or another object, if you toss a different thing, then like the probability of head may be different. So you have to define what you throw. And third, when you say 50%, it is attached to head, right? So we are talking about probability of head, not tails. So head is the event of your interest. So you are talking about the event of head, right? In this simple three components should be accompanied by any probability. When you talk about a probability, even if it's not explicitly stated, there must be an underlying experiment and an event of interest, right? So we are going to define a few more terms to study the structure of the probability. So let me define those basic terms. First, experiment. So this is just literally an experiment. There is no additional meaning in statistics. Experiment is a process leading to a random outcome. Whatever. It can be like a rolling a dice, it can be like coin toss, whatever. But so you have to define that to define a probability. And second, outcome. Outcome is literally an outcome, right? So it's a result from an experiment, right? Outcome. And sample space may be a new term. It's a this is the space. It's a collection of all possible outcomes, right? So, like in the coin toss example, it is easy to find what is an experiment, what is an outcome, and what is the sample space, right? There are only two possible outcomes from coin toss. Coin toss is the experiment. Then the possible outcomes are heads or tails. And then the sample space consists of head and tail. There are two possible outcomes. So sample space is the set of possible outcomes, right? So you can extend the same idea to any kind of experiment. Let's think about rolling a dice. Then the sample space include 6 outcomes, 1, 2, 3, 4, 5, 6, right? And suppose that you inspect a part or a manufactured part from a factory, if the part is defective or not. So if you inspect, then the outcome can be like whether the part is defective or not. There are only two possible outcomes, so the sample space includes defect or not. And if you play a game, then the outcome would be win, lose, or possibly tie. And then the sample space includes three outcomes. Customer survey. Depending on how you ask questions, you can make it like satisfied or not, or you can make choices between 1 to 5 or 1 to 10, or like maybe a scale of 100, whatever. So customer survey is another experiment. You choose a random customer, and then his or her answer is your outcome. And the outcome depends on how you construct the questionnaire. And household income survey. In this experiment, the experiment is to choose a random household and ask about its income, right? And then the answer is the outcome, but the answer can be any number, any non-negative number, right? My income is $1,000 a year, for example. Then $1,000 is an outcome, so any number can be the answer. Therefore, the sample space includes any non-negative number, right? So it's pretty easy to understand what is the sample space, what is the experiment, what's the outcome. So far, there is nothing special, nothing new, right? And then, on top of that, we can define probability this way. Probability is the proportion of times that an event occurs when an experiment is repeated many times. We defined an experiment and outcomes. So then what you have to do to define a probability is to repeat the experiment. If the experiment is repeated, then you observe many outcomes, and then out of those outcomes, you calculate the proportion. That is the probability. So this is also a very intuitive way to define probability. But what you have to pay more attention is many times the experiment should be repeated many times. So this may not be possible, but this is the key part to understand what's going on. So we will talk more about that now. So, and data. So in a similar way, data can be defined as the observed outcomes from the repeated experiments. So when you repeat the experiment, the results are the data. The outcomes are the data, right? So when you toss a coin like 10 times, then record the outcomes, then that becomes your data. Or if you survey 1,000 households and their answers, make a data like that. So data also assume repeated experiments. And then we call the number of repetitions as the sample size. So how many times the experiment is repeated, that's the sample size, which will be the same as the number of observations in the data. So if your data includes like 1,000 observations, that means the experiment has been repeated 1,000 times, so we call that the sample size is 1,000. And usually, almost always, the sample size is denoted as n, like lowercase or uppercase. n, the number of repetitions, n is the notation for sample size throughout this course, and maybe any textbook you read will have the same notation for the sample size. And the sample size is actually the single most important thing that determines the accuracy of your statistical analysis. If the sample size is too small, then there is no statistical method that can make an accurate result. So having enough sample size, having a large sample size is the most important thing in statistical analysis. But usually we cannot change the sample size because data is given. So we just assume that sample size is enough, and then we study what we can do. But if the sample size is super large, then actually you don't need any method. Just calculating probability or average should be enough in the case. Anyhow, so sample size, we learned what's behind is an experiment and its repetition. Repetition of experiment is important. So here, this is my actual simulation. I simulated coin toss. I calculated the probability of head, and so that means I throw coin once, twice, 3 times, up to 1,000 times on computer. My computer does the simulation. So I simulated coin toss, and each time I calculate the probability of head, or the proportion of head. That is, when I throw a coin for the first time, it was head. So the proportion of head was 100%. And second time I got tail, so the proportion becomes half and half, and then go up, down, So as you can see, it fluctuates. But in the end, it will be very close to the true probability of 50%. What you can see here is the importance of the sample size. Like this is a special example because we know the answer. We know the answer is 50%. Well, 50% is the true probability of a coin toss. And we can see that if you have a small sample size, like below 100, then it can be wrong as much as like 40%, like say. Even you throw 50 times, the probability can be like 10% point wrong, away from the true probability. But after a certain number of repetitions, the error is pretty small. So what you can see here is the importance of sample size. As the sample size increases, your your analysis will become more accurate, as you can see. And another thing, what you need to imagine here is that I explained this under the assumption that we know the true probability. Like, yes, we know the true probability in this example, but the main ultimate purpose of statistics is to estimate the true probability. Usually, we do not know what is the true probability in our data. So, we don't know where it is converging to. That's what statistics does, why we study statistics. And so repetition of experiment is important because it tells you where the truth is. So here I will distinguish two important concepts to understand statistics. First, as I said, in our previous example, there are two probabilities we compared. One is the true probability, 50%. 50% is the true probability we know in this example, but in general, true probability is unknown, right? That's one thing. And we compared the true probability with the probability we obtained from the finite observations, from the finite number of repetitions. So we are going to distinguish those two concepts. Population is the collection of all items of interest. In our example, in our coin toss example, population is the limit. If you throw a coin for an infinite number of times, that is the population, infinite coins. On the other hand, the sample is the collection of finite observations, observed items from the population, which is the data. So again, go back to this example. The true probability is obtained when you throw a coin for an infinite number of times, which is purely theoretical object. The infinity is not approachable. You cannot actually do the experiment that many times, but theoretically we can imagine that. So that is the population, the world of idea, the ideal experiment of infinite times. On the other hand, finite sample, depending on your sample size, like if you throw 500 times, then still it is finite. Even though 500 can be a large number, still it is finite. So we call that a sample. Still, that's a part of what we want to know. What we want to know is infinite size. We only observe like 500 or 1000. Still, it's small part compared to the true the population space. So simply speaking, you can understand the population is the set of observations when the sample size is the infinity. Of course, it is not possible. It is not possible in practice, but we can think of this. We will think of this because, as I said, this is what we want to know. In statistics, the ultimate goal is to understand and to estimate the population object, as if we repeat an experiment for an infinite number of times. So the truth is defined based on the population. So when I say true probability, true average, that means I implicitly assume that I could repeat the experiment for an infinite number of times, right? So in the end, our goal, like what we are going to do in our chapter, say 8, 9, 10, is to infer about the population based on a sample. So we have finite or small part of whole set, large set, but using the small part we observe, we would like to infer the whole shape of the population. That's what we are going to do in like what statistical methods are doing in general. So so far I have defined the basic conceptual framework to understand probability and more generally statistics. Now let's bring that back to more practical data, not a simple example as coin toss and not theoretical examples, abstract examples, but what you are going to use in practice. Most of the data you are going to use will be one of these two types. One is survey data. So survey is most common experiment in social science. So you know what is a survey. So survey is literally choosing a person or household, company, whatever, choose someone and ask questions and get the answer. That is survey. And it is an experiment it is an experiment, and the randomness is coming from choosing individuals or subjects to ask questions. You have to randomize the subjects of the survey, right? Otherwise, its experiment is not random. For example, suppose that you are wondering what is the average GPA of SUNY Albany students. Then you have to randomly choose the survey participants. But if you ask friends around you, then it is not random. So making a random choice is the key part in a survey. So it requires a very careful design of survey, right? And some commonly used survey data include panel study of income dynamics, and current population survey, and national longitudinal survey of youth health and retirement study, consumer expenditure survey, survey of consumer finances. So maybe you can guess what kind of data variables would be included in those data sets, and they are based on surveys. And these data sets are publicly available, and I'm giving you the list because if you're interested, you can use one of them, like some of them, right? If you're interested in like health insurance or retirement plan, then this data set would be a good source of data, for example. And another type of data you may use is time series data. So time series data is a little bit weird. So for example, let's think about this statement. The probability of rain on Labor Day is 30%. See, I say that sentence, you know what it means. But let's carefully think about what is the underlying experiment. So the sentence itself is not weird, but when you think about the underlying structure, it doesn't make any sense. How can we experiment like the rain, the weather, especially for a future date? How can it be possible? Yes, it's weird, and we need to imagine a hypothetical experiment. So put it this way. So the experiment is like this. There are a lot of possible weather scenarios. How the wind blows, where the clouds are, and what's the the temperature is. So there are different scenarios, and someone, say God or Mother Nature, chooses one of the scenarios for Labor Day, right? Of course, it's purely imaginary process, but another interesting thing here is the experiment is repeated every year on Labor Day, for example. And then, so every year on Labor Day, the Mother Nature chooses one random scenario. Then it is an experiment, and you observe repeated outcomes on Labor Day for the past many years. Or you can think it this way, God chooses a randomization happens based on the weather situation, like temperature and wind are similar. So then still the outcome can be different. So you find similar weather situations from the past and see what happened after the weather situation. So that's another way of understanding the repetition of this experiment. So right, similar idea can be applied to any time series data. For example, we are interested in what is the probability of stock market crash next year, or what is the probability of a recession next quarter, right? Something like that. And then we need to define probability, and we need probability. We need probability, and there is no problem in understanding the probability in this way. So we use this. And so as a last remark, so yes, I understand you may think this argument about time series experiment may be misleading or like absurd. I understand it's absurd, but so there are in statistics literature there are different approaches to define probability, like Bayesian approach. What I have explained is so-called frequentist approach. So there are many competing approaches to define probability, but it's less important for practical purpose. So no matter what the probability, no matter how the probability is defined, you know the meaning of the probability. So I intentionally I did not explain other approaches, and what I explained is the major the major mainstream main approach to define and understand the probability. Okay, so it was too long, and I'm going to continue in the next video. See you later. Bye.